Okay, so as usual, quick reminder that the HOLA experiment, we need to make sure that everyone is either starting up on it or has completed it. Let me go ahead and share screen here. So right here, the HOLA ChemX discussion and poster. And I'll keep reminding y'all every week, of course. However, we're getting closer to the end. So if you haven't started it, at least go complete the discussion. There's a lot of current submissions, which is great. But make sure that if you haven't done it, to get started, at least complete the discussion and start up on your poster, get a rough idea out there. We're getting into April now. And quick reminder, your poster is due May 1st at 11:59 p.m. So from today, we have about a month. Okay. And yeah, if you ever have issues connecting to the Zoom, please go ahead and try to connect through your phone or something, or try to connect early and just jump on, be ahead of the curve, so that way that we can get started, because it's early in the morning, pretty short lessons, so just try and get on it like 5 minutes earlier or a couple minutes early, so that way we don't have any little interruptions. If someone just pops up and says, oh, I'm running late, and we're in the middle of talking about the experiment, it's a distraction for the whole class. So let's make sure that we are not late going forward. And let me switch my screen share really quick over. So HOLA ChemX, please make sure to work on that. And let me switch over to our module today for what we are reviewing. So last week we did our SN1, SN2 reaction. This week we're going to be working with a gas chromatography. Switch that back. All right, so Group C, Week 8 online. Today is March 30th, and this is our gas chromatography section. So firstly, of course, we're going to review through our lab manual like usual. Secondly, please make sure to watch these videos. I will be reviewing one video with y'all today. I made some notes as to kind of where to jump to within the video, so I can give y'all small pointers, of just saying, oh, this is exactly what's happening here, and give you a visual representation with a good explanation that maybe isn't present in the video. But of course, make sure to watch these videos to get more of an in-depth understanding if my explanation isn't thorough enough for today. Thirdly, the pre-lab notebook will be checking here shortly. Fourthly, pre-lab quiz, make sure that's completed. And then we have all of our data here, which we can review at the end. So let me switch back one more time. And okay, let's see. So I am going to type in the chat and list out some people who I need to show lab notebook. So let's see. All right, so for Taylor, Deandra, Patrick, Jeff, Amy, and Madison, please either show your pre-lab to the screen, and let me see, I'm pretty sure I had the multiple shares. Yeah, so if you have it on your Word document, please pull it up on your Word document. Otherwise, please go ahead and show the pre-lab to the camera on paper. Okay, great. Yep. So just like usual, having everything prepared and procedure. Okay, great. You're good to go. Deandra, you can sit out. Okay, and this is Taylor. Okay, great. Looks good. Okay, next. So Taylor and Deandra, y'all are good. Okay, Patrick. All right. Great. All right, and next, let's see who's next. Okay, Amy.
Yes, I have it on paper.
Okay, and Jeff, you're good, and Amy, yeah, I can see. Looks good. Let me make sure I got everyone.
Yeah, I'm trying to pull it up right now. Give me 1 second.
Okay, great. And then if you just scroll up really quick just for the, okay, good. Yep, so awesome. Yep, so that's basically it. You just want to make sure, you know, you have your ref procedure, your hazards and everything like that, and good to go. Great. Okay, awesome. Yep, so that's basically it. So I think that was everyone. Yeah. So make sure, once again, if you are not sharing your camera right now, or if you have a screen that doesn't show that you're paying attention, then you will be receiving reduced points. It is part of the attendance just to make sure that, you know, everyone is fully paying attention towards the class period. And let's see, next we're gonna go forward, and I already went through the module. So like usual, we're going to go forward to review the manual. Let me just have this real quick. Okay, great. All right, let me get to the top of this. Okay, so this week we'll be studying gas chromatography, and we're going to go ahead and go forward to understand exactly what's going on. So firstly, it is another form of chromatography, spectroscopy, if you will. And in this way that, you know, we used something like silica gel to separate on column chromatography. In this situation, we're going to be separating compounds using gas chromatography. There are multiple components within the separation of compounds, and this is why this week we're going to be focusing on some very similar compounds, because looking through this, gas chromatography can be sorted by many different variables. So firstly, compounds present in a volatile liquid or gaseous solute are isolated after traveling through a coded column based on the substance's size and intermolecular interactions. So not only does it matter on how big that the compound is, it also matters on the functional groups. Is it polar? Is it nonpolar? So firstly, what exactly is the machine that we would be utilizing to perform gas chromatography? And that would be right here, our Vernier mini gas chromatography machine, or GC is what they call it by shorthand. It utilizes a metal column. And remember this part, it has a non-polar coating. So instead of the silica gel as a polar stationary phase, this non-polar coating will be our stationary phase. So in a way, it's like reverse phase chromatography, if we remember from the column chromatography section. Secondly, what happens is that we inject into the GC machine, and I'll show you in a video later, the sample, and it is carried through the stationary phase, which again is that nonpolar coated metal column, by atmospheric air, which acts as the mobile phase, just pushing it through the machine. So the reason that it sticks to the nonpolar coating depends on its polarity, right? So if it's more polar, it won't stick as much. If it's more nonpolar, it will stick longer to the nonpolar coating within the machine. Then what happens is that the organic compounds that flow out of the chromatography column, they're detected by a chemical sensor that produces electrical responses proportional to the concentration of the compounds. As you can see here, we have a graph with the X shown as the time over a portion of minutes, and then the signal, which is measured in millivolts in the Y-axis. So as we see here, the unique time it takes for a compound to exit the column after it is injected is called the retention time. So there's a retention time within column chromatography as well, but primarily here, the retention time is showing the factor of how long it takes for a compound to get through the gas chromatography machine. And so looking at it, we need to understand further, well, what makes it stick to the column? What separates multiple compounds? So one thing that we can look at is more volatile compounds, or compounds with a lower boiling point, will move through the column faster because they are flowing in the mobile phase and not strongly bonded with the stationary phase. So something less volatile or a higher boiling point will elute slower or have a longer retention time onto our gas chromatography machine. The surface functional groups present on the compound are also a factor. So not only is it the volatility, it is also depending on the functional groups. Is it, a long hydrocarbon chain? well, if it's a long hydrocarbon chain, that would want to stick longer because of the nonpolar column. However, if it's maybe something that's, extremely polar, then it would just want to go straight through, like something if we ran ether or acetone, as we will see later, it's very volatile. It's mostly polar, only slightly nonpolar, so it won't stick as well. It'll have less retention time, and it'll go through the machine very swiftly. So, for example, alcohols that the weakly bond with a polar stationary phase more than esters because alcohols are capable of forming hydrogen bonds. So in this instance, alcohols would go through much faster than an ether, not only because it's more polar, but also because it can form hydrogen bonds with the atmospheric air that's moving through the machine. Another thing that we need to also understand here is that the molecular weight of a compound may play a role to an extent. And in here they're saying it's not a direct relationship. However, if you think about it, if you have a 6-member carbon chain that's going into a gas chromatography machine, right? And you have a 7-member carbon chain. Well, the heavier the molecule, the longer it'll take to move through. So you can think about it like traffic. And if you have, an 18-wheeler versus a race car, if you have a race car, it's going to just cruise through. But if you have an 18-wheeler, it's going to take a while for it to get through the traffic. So, you just have to think about that molecular weight. It is relative in here, but it is still more so related to the polarity of the compound and the volatility of the compound. So there are multiple factors going into this. You just have to think about what is the relative rate and what is the relative importance of each type of characteristic of each compound. So when separating compounds with wide range of boiling points and polarities, what we can do is actually raise the column temperature during separation, and you can do it while the gas chromatography machine is going in order to elute it faster or slower, depending if you need your peaks to be more spread, or if you get one peak and then you're sitting at the machine for 20 minutes and nothing happened. Well, then you can raise your temperature more, and then maybe it only have to run for 5 minutes. And those are just things that we would mess around with in lab to optimize our time within research. But the changing of temperatures and pressures, we're not going to be doing in this lab. This is more so of a basic analysis and understanding of how not only to perform gas chromatography, but also how to analyze the data that we're given by, say, figure 1 here in the charts that will be given for your data. So additionally, pressure in the same way can be changed. High pressure can cause greater strain on the intermolecular interactions between compound and stationary phase, reducing retention time. So it would mean that something that's highly nonpolar will stick less because the pressure is pulling it through the machine more. So that is just another thing. So temperature, pressure, we can change these within the machine itself, but make sure the big thing is that nonpolar stationary phase, and think about the polarity of the compound you're putting into there. If you have a mixture, think about the polarities the polarity of each compound within the mixture. And then also finally, as well, we can think of the volatility, what has a lower, higher boiling point. And then the most minuscule thing we can think of is the molecular weight, which is most relevant if you're thinking about comparing two very similar molecules that maybe have one extra carbon chain or one extra, functional group added onto it. And then the molecular weight would take over as a precedence towards seeing the retention time. So what we would be doing is measuring and analyzing the chromatogram of a mixture of 3 compounds in a ketone mixture is what our data will be. Then we measure and analyze the chromatograph of each compound individually. And then finally, we'd measure and analyze the chromatogram of each fraction collected during the fractional distillation experiment. So this would be something we would have set aside from fractional distillation in order to perform the gas chromatography. So going through here, I'm not going to read through the full procedure because it's very straightforward. The only thing that I wanted to highlight on here, if you say something along the lines of, 1 microliter glass syringe or pipette or whichever way that you want to phrase this, just make sure that you have something near like 0.6, 0.5, or 1 microliter, 10 microliter, have it within the range. Just make sure that your syringe is very small when you write it into your glassware. There's only a few things in this lab. There's the machine, there's the gas chromatography, the Vernier Mini GC, there's the lab quest that connects to it, and then there's the syringe. And then of course you have all of your compounds, but those should be in your hazards section. So going through here, this is not too critical because I'm about to walk through the video with y'all. So I'm going to skip over the procedure and just tell you as we watch the video together exactly what's going on. And then finally, what we do once we get our data, we need to determine the area for each peak by measuring the height and width. And again, we'll review this within the video. The area of the peak is the same as taking the area of a triangle, which is 1/2 width times height. The width is measured at the halfway point of the peak. And once again, I'll show you that in the video. Then finally, to determine the ratio of each compound in a mixture, you need to take all the areas together as a total and then divide the specific compound that you were thinking of over the total area. So let's just say you have 30% acetone in your mixture, right? Then you would take the area of your acetone, add it to the other two compounds. You have a total area, and then you divide the area of acetone by the area of your total compound mixture, multiply by 100, and then let's say you have 30%, composition of acetone, for instance. So at this point, then you'll go forward, complete your post-lab questions. I know that some experiments, they've been weird. They've had data analysis as the statement. If you ever have a question regarding that, always just have your data analysis or post-lab questions, whatever they call it, just have it in that section so that way we'll have that as a staple. But for this week, it shows post-lab questions. So please complete those after this. And let me switch over to the video so that way that we can walk through that together. One moment. Okay, and I made some notes on here so that way that we can watch the video and I can just jump through to the most critical points that I believe are worth analyzing, because a lot of it is, like setting it up. Oh, I'm moving one thing over here to over there, which is not too critical. I do definitely recommend for you to walk through the videos that are in the modules, but this will just give you a rough understanding of the primary points that I want everyone to take home from today. So firstly, we're going to jump over here to the 20-second mark. This machine here is your Vernier mini gas chromatography machine, and they're setting it up in order to plug it in and have it attached to our lab quest. Here's our lab quest. Everyone's familiar with this, probably from Gen Chem at this point. So, we plug it into our mini GC, and then here's our adapter to have this plugged in. I'm going to go ahead and skip forward because, like I said before, a lot of it's just preparation. Okay, now here's our syringe, and this is pretty critical in terms of utilizing a calibrated syringe because we want to make sure we know the exact amount of compound we're placing into our machine. So for instance, this is a 1 microliter syringe. We're going to be pulling 0.2 microliters out. Here's our compound 2-butanone. We have our other ones, the ketone mix. We have our acetone here as well, that not only will we be using to clean out our syringe, but also to analyze, 2-pentanone. And finally, our ketone mixture. Okay, and then I'm going to jump over to 221. So here, they're utilizing the syringe, and then what she's doing is sticking the syringe into the acetone and pulling a little out. And then as you can see very lightly, it probably will come out better on your video whenever you watch it yourself. But all that's happening is pulling a little acetone in and then spraying it onto the Kim wipe so that way that you can flush out the syringe just in case there's any other sort of compounds that may be present in the syringe from the person who used it last. It's always a good method to clean it out with acetone as a base so that way that we know exactly what's going to be going into the machine. And acetone's great because it's amphiphilic. It's both polar and nonpolar, so it'll pull both water and hydrocarbons out of like given glassware. That's why we love to use acetone in lab. So next we can jump over to the 330-minute mark, because what happens here is this is the ketone mixture and they are pulling the ketone mixture into the syringe. The reason they do that is because it's good formality to flush out your syringe with what you're going to be using. So they flush it once with the ketone mix to maybe pull out the extra acetone, flush it twice to make sure that you have it very clean throughout. And then finally going forward, let me see where this is. Yeah, and so now we're going to be prepping the lab quest for the experiment. So see mode, gas chromatogram. We go over to this temperature pressure profile, and then we just leave it as standard. We're not going to be messing with that this week. So don't inject until the GC is ready. So the GC is heating up, the pressure is stabilizing. And you can see on the machine as well, GC not ready. Okay, and then let me see what's next. So here's a little bit of waiting, so we're going to skip ahead and go to the part right here. So now we have rinsed out our syringe a couple times with a ketone mix to make sure that's all we're going to be putting in this machine. We pull out exactly 0.2 microliters, and this is critical for the machine because it's calibrated to a specific size of compound that needs to go into the machine. So we press it into this plunger, and then we prepare the lab quest because we're simultaneously going to be plunging the compound into the machine and also hitting collect on the lab quest. So that way that the lab quest is collecting the data as you're putting the compound directly into the machine. You get a stabilized time of exactly knowing when it entered, and then they have placed the compound into the machine and it started to run. So this is another point where I'm going to skip ahead because it takes a little time for us to run this experiment. So our first peak is noted over on this video at 6 minutes and 30 seconds. So I'll give this a second to see, boom. Now it just shoots up and you get your first peak in your ketone mixture and a very sharp peak, and now it's gonna fall down. So we can skip ahead to 6:54. So here's our second peak, shoot straight up again, and it's gonna come right back down. Okay, and then our third peak is gonna be at 7:55. So I'm gonna jump ahead to there. So you see there's a lot of weighting involved within this too. So it's a lot different in lab when you're processing this and utilizing the machine in order to perform this experiment. But we finally get our last compound within our ketone mixture. And so going forward, once we've finally collected everything that we need to, and we have a nice graph ready for us, we can jump over to 9 minutes, 50 seconds. And this is when everything has been collected. We're done with it. So we zoom in so that way that we only get what we need. You know, there's extraneous time to the right, extraneous time to the left. You just zoom in for a good fitted graph. Then we take our lab quest over here to our printer. We hit File, Print, Graph. This is a good part here. You can actually change the graph title. So instead of having to write it in, you can put your graph title there. So in this instance, we're running ketone mix. For the next ones, we would be using acetone, 2-butanone, 2-pentanone. And the main thing I would say to think about, you know, while you're processing this, all of this, the acetone, the butanone, the pentanone, you know, review your organic chemistry and think about what's the difference between these. The main difference is molecular weight in this instance. The volatility, there definitely is a difference in volatility between those compounds. However, they're very similar. They're all ketones. They all contain one carbonyl oxygen. They're very, very similar. And so that's when we start utilizing our other methods, such as volatility, which is, you know, there's a couple degrees Celsius between each boiling point. The molecular weight is definitely different because we have added carbons to each side. And finally, our machine has printed and we get our nice clean spectrograph here. So what we can do is we see we have our time and signal. Let me pause this really quick and find where we go. So it's printed. Now we're going to go to the measuring portion. So this part, within the data that we give you, the compounds have been measured already. So you're just going to have to analyze this. So you make a straight line across the x-axis to, you know, give us a good basis of where we're going to measure from. Then what we do right here, you see you take a ruler, you measure all the way straight up to the peak from the base. And what that gives you is, of course, the height. So then we write down how many centimeters of height that is. So in this instance, this would be 10.4 centimeters. Okay, and then this is the critical part. So make sure you're paying attention to this because this is where people commonly make mistakes. What we do in order to get the width is we take the half point. So half of 10.4 at 5.2 centimeters up the ruler from the base. That's where you measure your width. You don't want to measure the width at the top. You don't want to measure your width at the bottom. Right in the center is going to give you your precise width of which that you can calculate your area. And it's the same way that you would be doing within performing, regular geometry. So in this instance, we have 0.4 as our width. And so now that we finally have that, let me go ahead and skip ahead over to, finally, we have all of our peaks measured. Let me pause it at a good point because it's kind of jumpy. And it's not coming out too clear here. But basically, you have your height of 10.4 centimeters, you have your width of 0.4. So then you do your multiplication, multiply the 2, divide by 2, you get your area of your first peak, then you add it to the area of your second peak, add it to the area of your third peak, then you have your total area of composition, right? Once you have your total area, you can divide each individual peak by that total area to get the individual percent composition. So for instance, you can see the third compound here is pretty large, decently tall relative to the rest of them. I would assume the third compound here is going to have a larger percent composition. Let's say it's 40%. Well, then let's just say the next one in the middle here is 35%. So then, 75%. So then that means only the very first one was 25% percent composition. So those are the critical points that I wanted to cover with everyone today. And finally, I wanted to take a quick peek over here at the data, just so that way that everyone can see where to utilize this. Make sure when you're in here, you come over, you can either go to pages or modules. Once this wakes up, here we go. Come all the way down, come to the week, gas chromatography, week 8, click into your module, okay? Make sure to watch your videos, of course, and then here's your data sets. So I'm not gonna go through all of them, but I'm going to show this one as an example. If your first name starts with A through D, then utilize this. If it goes with any other of the alphabet, please read through the bottom of the module and it'll show you exactly which data set is yours. So acetone, for instance here, 1 peak, you would calculate your area. 2 butanone, calculate your area. And then 2 pentanone, and you would calculate your area, of course. And then you can even see here from this is near a little bit less than 1 minute for acetone. For butanone, it's a little less than 2 minutes. And then for pentanone, it's over 2 minutes. So you can kind of start thinking about the molecular weights and understanding where the retention time comes into as a factor, and understanding the concept behind it of why. Why is always the question. And you think about polarity, the volatility, the molecular weight, what functional groups do we have on it? And then that's finally where we conclude our lesson with understanding an overview of gas chromatography. So make sure to utilize your data here. Please look through E through H here, I through L here, et cetera, et cetera. And if anyone else has any questions for today, I'll be happy to answer them. Otherwise, I'm going to stop the recording here real quick.